all. So now we are having the second speaker, eminent speaker, Dr. Shwetab Srivastava. Currently, he is working in a SMP degree college affiliated to University of Allahabad, he has completed his PhD from the Indian Institute of Technology, Kharagpur, under the guidance of the Professor D.K. Gupta. And he's published so many good papers. All the SCI scopus are indexed there. So numbers is not important, but the contribution is important. So as I started my work, so I connected. I saw the paper and connected, and now we are together. So yeah, so he's a peer review member. He's reviewing the papers and all. So hopefully the you all of you get understanding of the area of his research interest area by his talk. So now I now to invite to the Dr. Shwetab. Over to you, sir.
Okay, thank you, sir. Am I audible? Am I audible to everyone?
Yeah, we can see, we can hear you.
Okay. 1 second. Is it visible? Am I sharing?
No, sharing is not coming yet.
Okay, 1 second.
Again, you can try and the same first.
Yes. 1 second. Now is it okay?
Yeah, it's coming. Yeah, now we can see. Yeah, this is fine. Yeah.
Okay. So first of all, thank you so much, Professor Faiz sir. You presented very nicely, and we learned a lot. And most importantly, matrix equations and matrix sign functions. Thanks for your presentation. And I would like to thank Professor Hemant sir for inviting me for today's lecture. And I also thanks to my colleagues, friends, students, scholars, everyone who is here, who is listening this talk for this. Thank you. Uh, Title for today's talk is iterative methods for the computation of generalized inverses. Okay. So what I'm going to do onto this talk is going to be very elementary level. I mean somebody who wants to work onto generalized inverse or more specifically Murray-Penrose generalized inverse, their methods for the computations. So that will be useful for them because I have tried to show here the basics and very elementary things, how generally direct methods, what are the direct methods for computing these inverses, what are the iterative methods for computing these generalized inverses. And also I have included here one research paper. Mainly it is because Professor Hemant sir, he is working onto this paper that I published during my early career of research, and I think he has modified that work also. So this is one more reason to present this work. And time to time, I will also use pen tap, digital pen, to clear some doubt or to make you understand the concepts and theory behind this particular topic. And this will help you to initialize your research area in the generalized inverse. Also at the end, I have included one application of this area into compressive sensing and signal processing. I have published one work into this particular area. This is very nice and very new area, and that is actually the application, very nice application of this particular topic. Okay. So coming to the things, why we need generalized inverse. Okay. So before that, we are familiar with this particular problem, solving system of linear equations, Ax equal to b. We might have studied in our linear algebra or undergraduate course that if A is n cross n non-singular matrix, square non-singular matrix. Okay, by non-singular matrix, we know that the matrix whose determinant is non-zero or matrix having inverse, right? And B is given vector and X is unknown vector. Okay, so if this particular system has solution X equal to A inverse B, because inverse of A exists, A is non-singular, then we know that its general solution is given by X equal to A inverse B. We are familiar with this problem. But let's think about this case when A inverse may not be exist. Means A may be rectangular or A may be singular matrix where we cannot say about the inverse of the matrix. And what we still want to find out the solution of the system of linear equation in the form of capital XP. Okay, where what is X? It should be like that, it should behave like an inverse of A. Okay, so to deal with this problem, generalized inverse comes into picture. So what is now generalized inverse? So you see, as its name indicate, generalized inverse means something generalization kind of things are going on, right? So basically it is the generalization of the ordinary inverse of the matrix. What is means generalization of the ordinary inverse? That I will discuss later on. First, let me tell you about the definition. What is the definition? If A is any M cross N matrix, okay, then its generalized inverse is matrix X, which is of order n cross m. Of course, m represent the rows and represent the column in general, satisfying the equation, matrix equation AXA equal to A. So if you will ask me the general definition of generalized inverse, I will say if A is any m cross n matrix A, then its generalized inverse is the n cross m matrix X, which satisfies or which solve this matrix equation AX equal to A. Now, why I say this? It is generalizing the ordinary inverse. It because if you'll ask me what is the generalized inverse of the matrix which is non-singular. Okay, so if it is generalizing the non-singular matrix, then what do you think? What will be the generalized inverse of non-singular matrix? What's your opinion? If I'm asking you, what is the generalized inverse of a matrix which is non-singular, or matrix which is having inverse, right? Because it is generalizing. So what do you think? What do you expect? Uh, I mean, if suppose your A is um, matrix which is say Cm cross n, and X is the matrix which is n cross m. Okay, I'm saying this matrix X is the generalized inverse of A if it is satisfies this equation AXA equal to A. Now I'm asking question, what will be the generalized inverse of A? Means what is X for A if A is non-singular matrix? So let me give the answer if you are thinking. If A is non-singular matrix, then what it means? Inverse of A exists. Okay, so what we can do into this equation, we may pre-multiply by A inverse, right? So if I'm multiplying by A inverse onto to the onto this equation, pre-multiply, then what we will get? A inverse A, right? A inverse A can be taken as identity. So here what we got? XA equal to identity, right? Or I can say this X is equal to A inverse. So what you are saying here? If A is non-singular matrix, a matrix having inverse, then its generalized inverse X is nothing but ordinary inverse. Because of that reason, we may call it that it is generalizing the ordinary inverse of matrix. Okay, so this is one reason for saying this. Now, what another thing generalized inverse can do? See, this line says that if X is in matrix satisfying AX equal to A, means it is generalized inverse. Then this generalized inverse solve the system of linear equation AX equal to B because it satisfies the equation AXB equal to B. This means that this system of linear equation has solution capital XP, where X is generalized inverse of A. And further, it may characterizes the whole solution of this linear equation, which is given by this expression, small x equal to capital XZ plus I minus XAY, where Y is some arbitrary vector. So this can also be proved because the main motive of this lecture is just to give you total brief idea of generalized inverse, how it works, how it what is its application, so that if you are starting your career or if you're starting your research in this area, this may be very useful for you. This presentation may be useful for you. It's very elementary level. So now here what I'm going to prove is that how generalized inverse solve the system of linear equation Ax equal to B. What does mean that solving system of linear equation? Of course, it means that this solve this equation. It means this satisfies this equation. So I can prove that like that. First, I'm assuming that system of linear equation is consistent, right? I'm saying that the system of linear equation consistent means this equation has solution. What does this mean? We must lies what we say when we say that any system of linear equation Ax equal to B is consistent. What is the general condition? We might know that by saying consistency means B must be lying into range space of A, right? We are familiar with the graduate linear algebra course. So if I'm saying the system is consistent, though I can write b equal to a of z. Z may be some arbitrary vector. By this, b belongs to range A. And now consider this equation. AXB is equal to, we can write AXB as AXAZ. What we have done here, just in place of B, I have written AZ. Okay. Now further what we have, since X is generalized inverse of A, so we know that AXA equal to what? AXA equal to A, right? AXA equal to A. So we can write in place of here AZ, which is equal to B. So what
Excuse
we
me,
have
sir.
got, you got, you know.
Can you again repeat this step ax equals after ax equals to b?
Okay. Just 1 minute. What here I'm trying to say is that generalized inverse solve the system of linear equations. Okay, so if this system is consistent, means B belongs to range space of A. By saying that B belongs to range space of A, I can say like B equal to A of some Z. Okay, where Z is some arbitrary vector. Okay, now what we have done, I have considered this equation AXB. What we can write AXB? AXB equal to can be written as AXAZ. Why I have written here AXA? Because we know that if X is generalized inverse of A, then what is this AXA? AXA equal to A, right? That by definition of generalized inverse. So this become AZ and finally this B. So what we have proved that AXB is equal to B. So it means this satisfies this linear equation Ax equal to B. So I can say that capital XB is the solution of linear system of equation AXB. So finally we can conclude that this generalized inverse solve the linear system of equation Ax equal to B. Further, what I am saying that the most general solution is x equal to xb plus I minus xa y. This can also be proved very easily. What you have to just do, just check that whether ax equal to b or not. Just pre-multiply here a, what you will get axb plus here you will write a, then this term will go out and simply it will come out to be b. So in this slide, what we have told? We have told that the generalized inverse is the generalization of ordinary inverse of matrix. Because if you'll ask me, what is the what is the generalized inverse of non-zero matrix? I will say simply A inverse. Later on, what I have just discussed, I have discussed that it characterizes the system of linear equation Ax b equal to b because it solves that. Okay, any problem to here? Any questions at this moment? If you have, you may ask.
The last generalized solution is a kind of a convex combination type.
It's
This,
like it's like all the solutions in like infinitely many, because if suppose the system is solution and system has infinite solution, though this represent all the solutions, because y is an arbitrary vector. It's not like a convex combination, because what it is written here is simply like this. uh, Ax is equal to A, and this is the whole solution. X B plus I minus I is identity matrix B Y. So this shows that this if this system has infinite solution, so this is one part of that solution. It's not like a convex combination that I have taken.
okay.
Okay. Yeah. Any other queries you have?
No, so far. Yeah.
Okay. Okay. Okay, so now I will discuss existence of generalized inverse. Like if you have any m cross n matrix, we can compute its generalized inverse. So this result says that suppose A is any m cross n matrix and E is any m cross n matrix and P is n cross n matrix, then we know that this particular form we might have studied in linear algebra, the normal form. If A is any arbitrary matrix, we can reduce that matrix to the normal form by pre and post multiplication by elementary matrices and permutation matrices. So basically, this is written that form. If A is any m cross n matrix, and suppose its normal form is given by EAP equal to IRK00, okay, where of course R denotes the rank of the matrix, where E is the elementary matrix of order m cross m, and P is the n cross m permutation matrix, then its generalized inverse X can be given by this expression X equal to P. This is block matrix E, and we can see that this particular matrix, this X will satisfy equation Ax equal to A. So basically what this result says, this result says that if you have any arbitrary M cross N matrix, we can compute its generalized inverse by using this technique. This is the theoretical analysis about that, because for any matrix we can have this particular form, and once you have this form, you have its generalized inverse where L is any arbitrary matrix of order n minus r cross m minus r. So I can show that also, that how this satisfies Ax equal to A, and I will also apply this result to compute the generalized inverse of this particular matrix. I have taken A equal to say 1 2 2 0 0 2, and we will see how to compute its generalized inverse. Okay, just using this, by using this results. So just I will use pentap again to make it clear that the existence of generalized inverse. Okay, okay. So what we have done, if suppose you have A is M cross N matrix, then what we have to do first, we have to reduce this matrix into this particular form. This is which we call as normal form, which is given by like IR, K, 0 and say 0. Okay, so what you have to find is you have to compute E and P. You have to see what is this elementary matrices and what is this P. Once you have this E and P, your generalized inverse will be given by X equal to P times IR 0 0 L and E. So you can check here also. This will satisfy AXA equal to A very easily, because E is M cross and E and P both are non-singular matrices. And so from here what we can write here, from this expression, if I'm writing this as one equation, from here I can write A equal to, what I can write, A equal to, A can be written as A inverse. We know that elementary matrices are non-singular matrices, right? So I can write this as A inverse IR K 0 0 and here P inverse. Okay, and then just apply this AX, then just check this AXA will come out to be A. It's not difficult to prove, because E inverse E will come, that will be E, P inverse P will come, that will become your P, and the matrix that will come into between will give you this particular thing. Okay, so but let me focus on to the numerical examples, because that will make that will clear your confusion if you are having any. So I have taken this example, particular example, easy example for theoretical analysis. Let A is equal to, say A is 1 2 and 2 0 and say 0 2. So what is our aim? My aim is to construct a generalized inverse X by using the previous result. Okay. So first thing what we have to do, we have to reduce A into Hermite normal form, that we have studied in undergraduate course. So I am not giving you the process how to convert the matrix into this normal form. You know that what you have to do, just apply some elementary row operations to convert this into row reduced echelon form. Okay. Once you are able to convert that, you have to collect all the elementary matrices that will come out to be, and then you will write E as the product of those elementary matrices. So directly I am writing what elementary matrix will come out to be with that. The elementary matrix that will come out to be by converting this matrix into normal form. Its normal form is basically that we will get is, it will be like 1 0 0 1 and 0 0. This is going to be its normal form. So when we are converting A to this form, in this process, what the elementary matrix is that I am writing directly. This is 0 1 by 2 0 1 by 2 minus 1 by 4 0 minus 2, and this is 1 and this is 2. So this is the elementary matrix E. Okay, and permutation matrix are matrix which is obtained from the columns of the identity matrix. Okay, by looking at this in row reduced echelon form of A, you see this, just look at the leading one, and like this you have to just take the identity matrix column. So the P will come out to be your I2. Okay, so you have E, you have P, and you can check if you have E and P, then your X will come out to be your that I mentioned just previously, that X will come out to be your P is identity, so no need to write. This is your normal form 1 0 0 0 1 0, and this is your elementary matrix 0 1 by 2 0 1 by 2 minus 1 by 4 0 minus 2 1 2. Okay, and if you will multiply this, this will come out to be 0, 1 by 2, 0, and 1 by 2 minus 1 by 4 and 0. And you can check that AXA will come out to be A. Okay, so let me come to the slides. So what I have tried to discuss, existence of generalized inverse. What you have to do to show that, just if you have any arbitrary matrix M, sorry A, so you have to just write its normal form. If you are writing the normal form, in the process you will get E and P, then your generalized inverse can be given by these expressions. And I have given you one example, simple example. All you have to do is just reduce this matrix into normal form, find E, find P, then your generalized inverse will be given by this equation. And this, you will see that this will satisfy Ax equal to A. So this part shows the existence of generalized inverse. Any query at this moment?
So any question? So we can find out generalized inverse of any matrix.
Yes, sir, of course. For
Non-zero
any
matrix.
arbitrary matrix, we can find out generalized inverse.
Yes. Okay. I think proceed here. No question.
Okay. This is little background. I
Yeah,
will
there's a
discuss node. Yes.
so I thought there is a question. What is the question? Yeah, Dilan.
Yes,
Yes.
thank you. This novel matrices you got it by what do you say, by using
Right
singular
normal.
value decomposition or what? Just tell me the method. Sorry.
Okay. Could you please repeat the question?
Okay. The novel matrix, yeah, that you got.
Yeah.
It was you got it by using singular value decomposition or something else.
No, no, no. I didn't use the singular value decomposition. I just, what I did is, let me show you with the example. It's not singular value decomposition. It's like uh, you had this matrix and you are converting this matrix into normal form. How you are converting the matrix into normal form? By applying elementary row operations. For example, uh, if I want to convert this matrix into normal form, I have to put 0 here and here, right? So I will apply one row operation like R2 goes to
Like,
R2 minus
you mean
2.
Gauss, like a Gauss
Yeah,
elimination? You mean like that?
yeah, yeah, right. With
Okay,
the
okay,
row
okay.
reduce elimination. With this, I will
Good,
get
good.
elementary matrices. Yes.
Thank you, thank you. Sorry.
Okay. Okay. Thank you.
Yeah, right. That's fine. Okay, next.
Okay. So little background about this topic. So it's very old research area. It's not like it's a very new research area. Many people have worked here. So research work started from the 1903 when Fredholm was working on to the integral operator theory. And later on in 1920, Murray, he has also done some work, but his work was not much recognized unless until in 1955 when Penrose extended the work of Murray's and what he just established that if A is any M cross n matrix, okay, then any matrix X which will be of order small n cross M which satisfies these four equations, matrix equations. Equation 1 is AXA equal to X, 2 is XAX equal to X, third property is Hermitian property AX, this is conjugate transpose of AX is equal to AX, and XA conjugate transpose equal to XA. So if any matrix X satisfies these four equations, then that particular matrix X is called as the Murray-Penrose inverse of A. Okay, and you can see that this has already included one condition, condition 1, which says that Murray-Penrose inverse is already generalized units of A, but additionally it has some other things also with these equations. Okay, and again, once again, the question is, if you'll ask me, what is the Murray-Penrose inverse of ordinary matrix, which is non-singular? So I will say it's Murray-Penrose inverse is again a regular A inverse. Understand? Because this also satisfied the equation 1. So my this topic is this talk is mainly focused on to this Murray-Penrose generalized inverses and its computations, and some research paper I will also discuss onto this talk. Okay, these in the slides, I am trying to discuss some other generalized inverses. I am not focusing on to these generalized inverses. The main motive to discuss about them is at least you should be familiar with different kind of generalized inverses which satisfies different conditions. For example, Drazen and group inverse. If A is a square matrix, n cross n matrix, okay, then matrix X will be called as Drazen inverse if satisfies this matrix equation. AKXA equal to AK, XAX equal to X, and AX equal to XA, where K is basically called the index of A. Index is you can say it's a number, its smallest number, such that rank of A raised to the power K plus 1 is equal to rank A. Okay, so and this is another inverse which is called weighted Moore-Penrose inverse. So these are some different generalized inverses, because many people are working on different generalized. Some people are have published several papers onto this iterative method for the computation of these Drazen and group inverse. Some people have worked onto the weighted Moore-Penrose inverse, which has these particular definitions. So at least you should be familiar with these terms, because who knows, if you are starting work onto this thing and these terms may come to you. But I focused mainly onto the Moore-Penrose generalized inverse, and one more important generalized inverse, that is called outer inverse A to TS. Even Professor Faisal has also worked several research paper onto the computation of outer inverse, and I have also worked onto this thing. What is outer inverse? For any m cross n matrix A, it is n cross n matrix X which satisfies this matrix equation. X equal to X with range X equal to T and null space of X equal to S. So what is the main thing is that you have to pre-describe subspace T. T is the subspace of Cn and S is subspace of Cn. So this is particular inverse which will give you which will give the outer inverse, which will give the inverse of A. And what will be the main thing about that is its range will be the same prescribed subspace T and null space will be S that you will give. So why we study outer inverse A to TS, that will be clear with uh, let me show first this thing. Okay, why we are working on to outer inverse A to TS, because those who will start to working on this area, you may find many papers onto the computation of outer inverse A to TS. We say like A to TS, like outer inverse A with prescribed range T and null space S. The one reason may be this result. This result says that if A is n cross n matrix, okay, then Moore-Penrose inverse A DAG is outer inverse A with range space of A to A star and null space A star. It means that if you have any m cross n matrix, and if you will take T as subspace of Cn equal to range of A star, and if you will take subspace S as a null space of A star, then outer inverse A2 RA star NA star, which is like A2 TS, will become Moore-Penrose inverse. Similarly, if I am looking for Drazen inverse, so Drazen inverse is outer inverse A2T with respect to range AK null space of AK. So what happens is that we are trying to develop a method for A to TS, and for different choices of subspaces T and S, we can get the different methods method for this different kind of inverse. Just with one method for outer inverse, you can develop several iterative method for several kind of generalized inverses, just with different choices of T and S. Okay, so many people have worked on to this outer inverse also. Here in this example, I have just given you one simple example. You suppose you have A as a 5 cross 5 matrix, and I am giving you T as equal to say C4 and E equal to say span of this particular vector. So the thing is, just compute its outer inverse such that it will have range. If you will compute the range of that A to TS, it will come out to be C4, and if you will compute its S, it will come out to be this, okay, null spaces. So this is one simplest example. This will satisfy the equation x equal to x, where x is A to TS, and its range will be T, and its null space will be S. Okay. So this is something, maybe it may be some typical, but in brief, I would say, if why what's the benefit of A to TS is that it's like most generalized way. Once you have the method for A to TS, you can have method for different other generalized inverses for different choices of T and S. Okay. Any queries here at this moment? You may ask. These are the different generalized inverses that I'm not going to detail, because I'm mainly focusing on the Moore-Penrose generalized inverse.
Yeah. Is there any question? I think at the moment there's no question.
Okay. So now coming to my main topic, Murray-Penrose inverse, its properties and its existence, and later on I will discuss about the iteration method for the computation of Murray-Penrose inverse. So the first important property about the Murray-Penrose generalized inverse is that for any m cross n matrix, uh, Murray-Penrose generalized inverse is unique. Okay, compared to other generalized inverse. Like if I'm simply talking about the generalized inverse, which satisfies only one equation, like axa equal to x. Murray-Penrose inverse satisfies all the four equations. So this says that generalized inverse may not be unique. For any m cross n matrix, we may have infinite generalized inverse. Okay, but if you're talking about the Murray-Penrose generalized inverse, means it is generalized inverse, but with some additional, it also satisfies some additional matrix equation. It is unique. Okay, I will prove also that how the Murray-Penrose generalized inverse of any m cross n matrix is unique. And also, as I discussed earlier, if matrix is non-singular, then its Murray-Penrose generalized inverse is just regular inverse that we know. Okay, so let me uh, let me show you how this Murray-Penrose generalized inverse of any m cross n matrix is unique. Okay, so okay, let suppose you have A. Suppose A is C by C. I mean this complex field, complex vector space. Okay, so if A is m cross n matrix, and suppose it has two Murray-Penrose inverse. You understand? I have to prove that its Murray-Penrose inverse is unique. Suppose there are two matrices B and one matrix is say C. Both are Murray-Penrose inverse of A. Okay, so by saying that mean that B is the Murray-Penrose inverse of A, I simply mean that it will satisfy all those four equations. What are those four equations? Like A equal to A, and BAB equal to B, and AB star equal to AB Hermitian property, and BA star equal to BA. Similarly, if I am saying that C is also Murray-Penrose inverse of A, so I mean that this will also satisfy this four matrix equation. I mean ACA equal to A, CAC equal to C, and similarly AC star means a conjugate transpose of AC is equal to AC, and BC conjugate transpose equal to BC. Okay, so what is our aim? I will show that if B and C are Murray-Penrose inverse of A, then B must be equal to C. Okay, so to prove this, it's not that much difficult to prove this. What we can do, we can start with the matrix. Say consider this matrix B. What we can write here, we can write in place of B as BAB. How I can write B equal to BAB? Because B is the Murray-Penrose inverse of A, so it will satisfy Penrose equation 2, which is BAB equal to B. Okay, further what I can write, in place of BA, what we can write, A star B star B. Now you may say how I can write B A star B star, because of these things. Okay, because we know that BA star is going to be equal to BA, right? So this A star, yeah, this A star B star is nothing but what it is. It is simply BA star, right? So BA star equal to BA, and this BA star can be written as A star and B star. So understand how in place of BA I am writing this A star B star just using these equations. So many theory is being developed just using this Penrose equation. Many methods are developed using this Penrose equation that I will also discuss. The main motive is this, how the methods are being also developed for computing Murray-Penrose inverse just using these four equations. Okay, so this is okay. And similarly, I want to introduce C also. So what I can do in place of A, what I can write? I can write A as ACA, because C is the Murray-Penrose inverse of A. So what will happen? ACA is going to be equal to A, Penrose condition 1. Okay, so in place of A star, what I can write? ACA star and B star B. Okay, and once again using conjugate property, what we can write like this here: A star, C star, A star, B star B. Okay, and in place of AC star, what we can write? We can write simply it as a CA, because AC star equal to what? CA whole star, and CA whole star is going to be equal to CA by Penrose equations. Understand? So what we can write in place of this here? CA star, A star, B star, D. Okay, and this is basically equal to what? CA simply B. Okay, because this A star B star is what? This is again you can write in place of this A star B star B. What we can write? This is equal to BA star B. Okay, and once again we know that BA star is equal to BA because B is the Moore-Penrose inverse of this. So this is equal to BAB. Okay, and once again since BAB is equal to B, so in place of this I can write B. So here I have written what? B equal to CAB. This we have done. Okay, similarly I could start from C equal to CAC because C is the Moore-Penrose inverse of A, so it will satisfy this equation. So using the similar procedure that we have done here, we will see that this is coming out to be CAB. And at the end, what we have just proved, B is equal to C. So what this result says, if A is any arbitrary M cross N matrix, okay, and A DAG, this notation is basically, we call this as A DAG, okay. So if A DAG is the Moore-Penrose inverse of A, then its Moore-Penrose inverse is coming out to be unique inverse, okay. And if the matrix is non-singular, then of course, if you ask me what is the Moore-Penrose inverse of non-singular matrix, then it is simply a inverse, understand? And now I'm discussing some of the direct methods for the computation of Moore-Penrose inverse. So this is direct strategy. If A is say M cross N matrix whose rank R. We know that for any matrix A whose rank is R, we have studied, maybe we have studied in undergraduate linear algebra course. We can factorize A. This is called rank factorization of A. So once you are able to factorize matrix A like FG, rank factorization, then its Moore-Penrose inverse is coming out to be this expression G star F star AG star minus F star. If you will check this A DAG, this A DAG will satisfy all those Penrose four equations that we know. And this is one another direct way. Suppose because we may come across matrices which are full rank matrices. We may come across matrices which are rank deficient matrix. For example, here if A is of full rank equal to n, means here I'm talking about the full rank matrices. Then its Moore-Penrose inverse is given by simply this expression, because if A is of rank n, okay, then this matrix is coming out to be non-singular. And I think we have seen one equation called normal equations, where in statistics also this equations arise, like you are trying to solve A transpose AX equal to B. Okay, then its solution is what? A transpose A inverse A if A is of rank n. Okay, and that particular thing, this expression is nothing but it is a Moore-Penrose inverse of A. Similarly, if rank of A is M, full row rank, then it's Moore-Penrose inverses. Directly you can compute using this formula. You can verify also that these expression will satisfy these four equations. Okay, so the next thing is any question till this point?
Any question for this part? Yeah, Saurabh. Yep.
Yes. Yes, sir.
Yes, sir.
Yes, sir.
Sir, that there are so many generalized inverses are there. Like I'm saying that the procedures are like Drazen inverse.
Yes, yes, yes.
Then Moore-Penrose inverse.
Of course.
So I heard about like 6 methods that around are there. So can we what is the like can we arrange the as the importance basis like in practical or something, so that we can focus on this method or that method for the initial, because I'm very interested to work on this generalized method for my near future. So that's what I'm.
So means you want to ask which inverse to focus on, right? I mean,
Yes, sir.
you
Yes.
you want to ask whether to work on Moore-Penrose inverse or whether to work on Drazen inverse, something like that, right?
Yes,
Am I
sir.
right?
Yes, sir.
Okay.
Yes, sir.
So I would say I cannot give. I'm not biased like you should not work onto the Dragon inverse, because different inverses have their own applications. For example, Dragon inverse has its own application. I have seen that many research paper where they will focus on the Dragon inverse solution of system of linear equations. Means you have a system of linear equation Ax equal to b. Here I am discussing about its solution x equal to a dag b, where a dag is the Moore-Penrose inverse. But even I have also worked on to one research paper where I have tried to find out the method for computing the Dragon inverse solutions. So because Dragon inverse has its own applications, you see that it satisfies less matrix equations. Like even Dragon inverse have applications like application of solving differential equations with constant coefficients. You might have seen expression of the form ax dax plus bx dash equal to f, where A, B are the singular matrices. So I cannot say that you just particularize any particular inverse. If you will work on to any particular thing, like if you are working on Moore-Penrose inverse or generalized inverse, automatically you will get the idea that you can extend the similar result to other inverses. Okay, if you are working on to say this outer inverse A to TS, what will happen? It is quite possible that first you will work on to the Moore-Penrose inverse, and based on that you may see that you can modify that result bit, and you can publish or you can do some research onto the A to TS. Okay, both all these are related to each other. So you work on to any particular matrix inverses that will benefit you to other also.
Okay. So one more thing, sir. You like share a slide that connect that generalized inverse with with other inverses.
Yes,
So
yes.
so if I worked in suppose one area, so
Okay.
somehow it is connected to other areas also.
Yes, yes, of course,
So in
definitely.
that sense, is it so? This is not an issue that much.
Yeah, it's not an issue. Even I have seen papers like people have worked onto the Moore-Penrose, like they have computed the iteration method for the computation of Moore-Penrose inverse. Okay, and that the just with simple modification to that method, they have applied that same method to the computation of outer inverse A to TS. Okay, so this way they may have some other papers also. So it like more generalized paper here they got. So you can go that way also.
Okay, sir. Thank you very much.
Okay.
So all the
Any other
areas are
question?
challenging. All the areas are challenging.
Yeah,
Very
yes, of course. Sir. All the areas are connected. You just work on to some particular thing, and this will benefit you to other problems also.
yeah. Any other question for this part? Oh, I think you can go now.
Okay, sir. Okay. Okay. So this problem. Uh, Let me do one thing. Yeah, this one. This I think most of you are familiar with the singular value decomposition. Even I have heard Dr. Mukul, he was talking about the singular value decomposition and then pseudo inverse, right? Direct method for the computation of Moore-Penrose generalization. The most you can say famous method is like direct method for the computation of Moore-Penrose generalized inverse is singular value decomposition. Okay, what is that? If A is your m cross n matrix, then we can decompose it for any m cross n matrix. We can decompose it as matrix like A equal to U dV star, where U and V are the unitary matrices of appropriate order. So this is particularly called your singular decomposition, right? And if you have the singular decomposition of A, of course you can compute. Then using this, the Moore-Penrose inverse of A dag will be given by this expression V D dag U star. Okay, so what is D? D is the matrix which consists of the singular values of A. So I will write this in detail through PenTab. So through this also says that existence of Moore-Penrose inverse means if you have any matrix, you have its singular value decomposition, and then you have its Moore-Penrose inverse, which will give which can you can compute by this expression. Understand? So I have also applied. In fact, what I say is that if you use many softwares like Maple, Mathematica, and MATLAB. So they have inbuilt function like in MATLAB. I know that this inbuilt function is PINVA that compute the pseudo inverse. We can also call pseudo inverse sometime to the Murray-Penrose inverse that compute Murray-Penrose inverse of A using this SVD decomposition. So here I have taken one simple example. This matrix I have taken, and I want to compute its Murray-Penrose inverse using SVD. Okay, so this will clear you a little more doubt that how the SVD is applicable to find out A. If you will use the MATLAB, then you can see that you just put A, then so you can get U and V separately you can get. And what is U and V? U and V are basically they are made from the singular vectors of A. U is the left singular vector of A, and V is the right singular vector of A. I will discuss all these terms through this particular problem. So in the next what I am going to discuss how to compute Murray-Penrose inverse of this matrix 1, 2, 2, 0 and 0, 2 using singular value decompositions. Okay. Okay. So the matrix A that we have taken is equal to 1, 2, 2, 0 and 0, 2. Okay, so this matrix D is basically this consists of the singular values of A. So first thing we can compute what is the singular value of A. Singular values are basically the eigenvalue of A transpose A. It means this matrix A transpose A, its eigenvalues are called the singular values. I'm sorry, square root of the eigenvalues of A transpose A. Okay, so eigenvalue of A transpose A, if you will compute, then it will come out to be 9 and 4. These are the eigenvalues of A. And if you will compute its square root, so then square root will be 3 and 2. So it has two singular values. When notation for that is basically sigma 1 and sigma 2. So D, the matrix D will consist, its diagonal entries are basically the singular values of matrix A. So we will keep this in our mind. The singular values of A are this 3 and 2. And the thing that we have to compute it, what is U and what is V, so that we can have A equal to U D V star. Understand? So for computing U and for computing V, you have to focus on the singular vectors of eigenvectors of A. Okay, so how this U has been formed? Basically, U has been formed from the eigenvectors of A transpose, or if it is complex matrix, I can take conjugate transpose. Okay, and V is basically formed from the eigenvectors of A transpose A. Okay, so now I'm not going to compute here eigenvectors because we are familiar with the how to compute the eigenvectors of A transpose or A transpose A. Just the main thing is what are the elements of U, what are the elements of V, what are the elements of D. So we have to keep in mind like singular values and eigenvectors. Okay, singular values of A transpose A and the eigenvector of A transpose and A transpose A, because these will form the column of U and V respectively. Understand? So with this, I have computed this U and V. I'm writing directly. You come out to be, if you will compute, this will come out to be 3 root 5 and 5 to 4, 0, 6 minus 3, 2 root 5 minus root 5 and minus 2 root 5. This is U. Just simply eigenvector I have computed for the matrix A transpose, and I have wrote them into the columns of U. Okay, and V is coming out to be 1 by root 5 and 1, 2 and 2 minus 1. This we have computed. This is V, and your D is equal to, D consists of, okay, D is like it's like a block matrix C0. Its diagonal entries are eigen singular values of A. Okay, so this is your singular value decomposition of A. And then if you want to compute a DAG, it is simple. All you have to do is simple matrix multiplications. It's not a big thing. Only one important thing is how to compute d DAG. Okay, so for computing d DAG, only what should we do? It's like an inverse. Okay, so just invert this diagonal singular value. Just you have to invert this, and in place of 0, just write 0. So how to compute d DAG? Invert these singular values and get the matrix, and then do the transpose of that matrix. Like if you will invert 3, it will come out to be 1 by 3. If you will invert 2, it will come out to be 1 by 2, and 0, leave 0 as it is, and then do the transpose. Okay, then what you will get simply 1 by 3, 0 and 0, and here 0, 1 by 2 and 0. Okay, so you have u, you have v, you have d, you have d DAG, and if you have these things, by this expression, you have the Murray-Penrose inverse of A. And this basically principle is applied in MATLAB. They use basically SVD to compute Murray-Penrose inverse of A. So this also says that the existence of Murray-Penrose inverse, like for any arbitrary matrix, we can compute its Murray-Penrose inverse by using SVD. And it is direct method. It has some computational for larger matrix, maybe it has more computational cost. Okay. Okay. So now what I'm going to discuss is what is the importance of Murray-Penrose generalized inverse? Why we need? But this is one reason. There are several reasons, but one important property of Murray-Penrose generalized inverse is that it gives the least squared solution of Ax equal to B. Like you have problem Ax equal to B, X is Cn. Then suppose the case where we may have seen that sometimes we may have system of linear equation having infinite many solution. Like suppose A is M cross N matrix, okay, and its rank is say less than N. Okay, so the system have infinite solutions. Understand? So what is the good thing about the Murray-Penrose inverse solution? X equal to A DAG B, right? I'm saying that this solve this equation. Because this has something important thing. It gives the least square error solution. Means from amongst the infinite solution, this will give the solution X, which will give the least error in terms of the L2 norm of Ax minus B2, which is actually the need, right? If you have infinite many options, what options you will prefer, right? You will prefer those options, or you will prefer those solutions which will give the minimum error. So the Murray-Penrose inverse give you the least square solutions to the problem. And also I can prove this, how this Murray-Penrose inverse will give you the least square solution this problem. Uh, Let me just prove this. This will give the more insight about the Murray-Penrose inverse solutions. Understand? So what I'm doing here, what I'm telling here is, suppose you are having Ax equal to both this linear system of equation, and I'm thinking about the solution X equal to A DAG B, Murray-Penrose inverse solution. What is the specialty about this solution? Specialty is that this gives the least square solution to this system of equation. What is the meaning of saying least square solution to this system in mathematical sense? Mathematical sense, it means that suppose you have X, so many solutions of these equations, so, and you are computing norm of Ax minus B, okay, and suppose you have X0, which is say X0 equal to A DAG B, right? Murray-Penrose inverse solution, and you are computing norm of Ax0 minus B. Understand? So what is happening here? You will find that this norm of Ax minus B must be greater than or equal to norm of Ax0 minus B. Okay, so in sense of L2 norm we have taken, I'm not writing here particularly. And this can be proved also very easily. It's not very difficult to prove. So I am just writing here for the sake of brevity. You will get a better insight. I'm going to show that how the Murray-Penrose inverse solution is going to give you the least square solution. Okay. So to prove this, I will prove that inequality that I have just shown to you. Okay. So how I'm going to prove? I am going to consider norm of Ax minus B square, where X is any solution to that problem. And my focus is on to this solution, X0 equal to A DAG B. Okay, so we can write this norm of Ax minus B. What is this? Before that, let me write one thing. We can write Ax minus B as ax minus, I can write like ax minus a plus b, and plus uh, ax minus b, and minus a plus b minus b. Okay, let me tell you what I am going to say. I am saying that I can add this term and subtract this term. B I will add because I have to introduce that thing, right? So I can write this as ax minus b, and minus uh, a plus b, and plus a plus b, right? I can do like that, right? So now take these two terms, ax minus a plus b, just take common a. So in place of this, you can write x minus a plus b, and just take these two expression and take b as a common. Then what you can write here is I minus a plus b. So now Moore-Penrose inverse, this is also came into picture, and this is now my ax minus b. Understand? Now what I am going to consider, norm of ax minus b whole square. This is, we might have studied in function analysis previous course, the Pythagorean theorem. With this theorem, I can write this is equal to norm of a x minus a dag b square plus I minus a plus, and this is my, okay, b square. Okay, and that term I am not writing because these are orthogonal vectors, so so that will cancel out. And you will see, if you will simplify this thing, you will see this is coming out to be norm of a, and I can write this as, because this is your x0, right? X0 equal to a dag b, so we can get this as norm of a x minus x0 uh, square, and also this is your the next side, this is coming out to be a x0 minus b whole square. You understand? So with this, if I'm writing this, norm of ax minus b whole square is equal to these sum of these two terms, both are positive, then what inequality we will get? We will get from this equal to norm of ax0 minus b. We can get from this inequality. So what we have just proved is that, you see, the Moore-Penrose inverse solution gives the least square solution. That's the thing that we have just proved that. Okay, so this also tells the importance of Moore-Penrose generalized inverse solutions among all those solutions. Okay, any queries to this thing? This was one of the main reason to study the Moore-Penrose inverse, something like that. Any queries you have, then you may ask at this moment.
Sir, I have one question, one doubt, sir.
Yeah, please.
I'm Professor Valamati from VIT.
Yes, yes.
Sir, regarding the representation AX is equal to B, is it the linear mapping you mean to say, sir?
Of course, if you have ax equal to b, then corresponding here I cannot say it's a linear operator. Here A is m cross n matrix, so I'm not particularizing thing that A is a square matrix. A is arbitrary. It may be linear transformation from Vn to Vm. It may be linear mapping also. Both things are possible.
Sir, this SVD generally will be using it for pre-processing in machine learning for
Yes, of
transforming
course, right.
data. So
Right.
this whatever methodology you are saying, this will give better than that of SVD, sir?
Yeah. Actually, what exactly is the thing is that later on I will discuss. At this moment, I have just discussed about as you know that SVD is a direct method to compute
Yes,
through
sir.
networks, right? So what I'm going to discuss is the iterative approach to discuss this, the same thing. So one advantage of this iterative scheme over that is that it has less computational cost. You will see that I think SVD has order n cube something operations, and you will see the most general method that I will show you, like Newton's iteration method for computing Moore-Penrose inverse, has less computational cost. So in terms of computational complexity, you may have less computations. So both have their advantages and disadvantages based on your requirements. So you may try using these iterative method also for your problem. You may get some good result also. It's quite possible.
Okay. Thank you, sir.
Yes.
Thank you, sir.
Yes. Yes. Sure. Any other questions, please?
Thank you, madam, for question. Any other question? I think no. You can proceed.
So how much time is remaining for me, at least?
It's up to you, but if you see the up to 2, we are having the 15 minute. You can take your time.
Okay, 15 minutes at least. Okay. Okay. So now I have given some literature review. I'm not going into the detail. I'm just here mentioning that how the research is going on. About them, I have already mentioned. You see here, because Sohail, I think Sohail has asked the question, right? That if I'm working onto this particular area, then how that is going to be useful. You see that how the people are doing research. Many new papers have also come that I haven't included here. Like some people have worked on the computation of Murray-Penrose inverse. Many people have worked on the Rajan inverse, outer inverse ATUTS. And even they had extended that to the operator theory also. Like finite, you may go from finite dimension to the infinite dimension as well. And our respected professor is also, I have also learned a lot from his research paper. He has also developed several higher order iteration methods for the computation of outer inverses and Murray-Penrose generalized inverses. And many times he has used the thing like he developed a higher order iteration method with the less number of computations. So for different kind of generalized inverse, many people have used different way to publish the work. So if you are working on to one particular problem, you may use that thing to other inverses also. It is quite possible, and this is the most general. Okay, if you have developed the method for the outer inverse A to TS with the suitable modification, you can get the method for Murray-Penrose inverse, Rajan inverses, and other inverses also. Okay, and now this is the next part. This is the research part that I have started my research work with this particular paper actually, and the paper that I am going to discuss, our professor Hemant sir has modified that paper. I have seen the result. I will go into more detail. So I thought of discussing that paper also here. That will be good for him and for maybe for everyone. So how I motivated this method. Iterative Petkovic and Stoyanovich, they published one research paper in Journal of Computation and Applied Mathematics in 2011 for the computation of Murray-Penrose inverse, which was based on Penrose equation 2. I mean, using these two conditions. This you might know that this is the Penrose condition 2, and XA star equal to XA. This is the Penrose condition 4. Using these two conditions, they developed this iteration method for the computation of Murray-Penrose inverse. Xk plus 1 equal to 1 plus beta xk minus beta xk a xk. Okay, where xk plus 1, yeah, xk is what? Sequence of approximation for the computation of Murray-Penrose inverse. Okay, so this is an iterative scheme, right? Now this is iterative scheme, and if it is iterative scheme, of course we need initial approximations. So the initial approximation to start this iterative scheme is given by x is not equal to beta a star. Okay, a star is a conjugate transpose of a, and beta is any real number between 0 to 1. And how to choose beta is given by this expression. This is a maximum of 1 minus beta lambda I a star a star. Lambda is the eigenvalue of a star a star. Okay, so using this expression, they choose beta. So one way to get the beta is what beta equal to, if you take 1 by norm of a squared, then automatically that will satisfy this particular expression. So when we develop code in general, what we do, we take beta equal to 1 by norm a squared. So this lies into this limit, understand? And we have initial approximation and we can apply this. So I can tell you that how they develop this method using these two equations. So the reason for discussing is that how the method are being formed. So one question I also asked from Professor Fraser that how by solving matrix equation we can develop a method for computing matrix inverses also. So here what I'm going to show, I will show that how this method came into picture. So maybe you may be able to publish some new method based, maybe you may get some idea and you can write your own method, and this may be beneficial for all of us. Okay, so let me prove this. How to get this method xk plus 1 equal to 1 plus beta xk minus beta xk a xk. Okay, so what he just taken into consideration. A is, say, any m cross n matrix, and X is, of course, n cross n matrix, and we are calling X as, say, Murray-Penrose inverse. Okay, we want to develop an iteration method for the Murray-Penrose inverse, but I will develop, not I, of course, that those professors, they developed that iteration method by using these two conditions. You can see this is the Penrose equation to Xx equal to X and Xa star equal to Xa. So let me show you how this method came, how this method has been formed, and then a very nice research paper onto that. So it starts with this. First, we have taken X equal to Xax, so I can write like X equal to Xax. Okay. Now, in the next step, let's take conjugate transpose onto the both sides. So let me take conjugate transpose onto both sides, X star equal to Xax star, and what we can write after that, this is equal to X star, okay, and this is equal to, we can write X, sorry, that's not like that. Yeah, right. What we can do, just take it like a one matrix like this. We can write the same thing as AB star equal to B star A star. You might know that. Take it like a single matrix X. So this is can be written as X star and XA whole star, right? So first what I write, we can write X as Xax Penrose conditions 2. Then I have taken conjugate transpose onto the both side, and then I have used the property of conjugate. I have written like that. Okay. Then what do you know that? You know that already X star equal to Xa. No problem at all to this. So this is one expression that you will be having. Okay. Now consider this equation. For arbitrary beta belongs to I. Initially, I'm taking beta as arbitrary real number, and I'm considering this equation. X star can be written like that: X star minus beta X. Oh, sorry. Beta X star Xa minus X star. You see, if you will write X star equal to X star minus this is what? This is plus beta X star. Okay, and you have just shown that this whole thing is what? X star. Just see, right? This whole thing is what? X star. So basically what it is written? It is written as minus beta X star plus beta X star, right? So basically I can say that this expression is right. So see how this beta came into picture, right? How I have told, what we have done, let us take beta is any arbitrary real number, and we can write this expression because we have applied Penrose equations 2 and 4. Okay, so if you will simplify this expression, I'm writing the end line. If you will simplify this expression, then you will get X star equal to X star I minus beta Xa plus beta X star. Okay, and since we are interested in X, not X star, so what you can do again, you can take conjugate transpose again on both sides. Then what will happen? You will get X equal to I minus beta Xa star X plus beta X, right? And from here, from this expression, we can develop iterative scheme that can be given as xk plus 1 equal to I minus beta xk plus 1 A star xk plus beta xk. Okay, and then he has used one property like this property in his paper, like xka star is also equal to xka, and using this the method he has developed that I have shown here come out. Okay, so you see here what I am trying to show that. I'm trying to show that how they use, by using these two equations, a new iterative method came into picture. Okay, and in this method, this is the way to take the initial criteria. And what we did after that, that was my first research work actually. I was just reading this paper, I was trying to understand this, and I observed this thing. Yes.
Sir, can I have one doubt, sir.
Yes,
Sorry,
please.
to interrupt.
Yes,
Sir,
please.
that expression you have written, no, sir. Can I see
Yes.
that? Handwritten.
Yeah, this one.
The previous
in
one you
Pentab?
have written. Yes, sir.
Yeah, okay.
Yeah. So actually, whatever you have given in that x star is equal to x star, when you are trying to equate both the sides x star, but
Yeah.
when you are trying to take it as an iterative part, the next state, I mean, next state x of k plus 1 is equal to some expression into x of previous state plus beta into the previous state. That formation you are doing now, sir. How we can relate the previous and the present as a single expression?
Previous if you have means if you just take an idea from the non-linear equations kind of thing, you might have studied Newton-Raphson method and fixed point iteration method, right? How we develop their method, like if you will write about the Newton's Raphson method iteration function, you might have seen like that when we were proving that it was coming like it has of this particular form, x minus fx dash f dash x. Okay, and then we develop iterative scheme like xk plus 1 equal to xk minus fxk by f prime xk. So this idea actually comes from there. Okay, so
sir,
the
this
same
may
thing.
be, sir, what I mean, even this Newton-Raphson method, if at all any, I mean, erroneous thing we are supposed to consider, that can be considered by f of x by f dash of x by including x with, I mean, the actual data is equal to original, I mean, whatever we have, I mean, received data minus the erroneous one. F of x divided by f dash of x is going to give a erroneous one, right, sir?
Okay. Of course.
So,
And here the thing is like that I also discussed with the first sir. This can be developed through like the most general case is the Newton iteration method. It is actually the particular case of that method,
sir, for
Newton's method.
Newton-Raphson, because what I understood about the Newton-Raphson method is how we are going to approximate the I mean given data to the actual one.
Okay, right.
Whereas whatever expression you have given, the next state, is the next state or is it the approximation state, sir? Whatever
Yeah,
iteration you are doing.
yeah, it's like that.
Okay, got it. Maybe the approximating the erroneous
Yes,
one.
approximating, right, exactly.
Okay,
Yes,
sir.
yes.
I got it. Thank you,
Okay,
sir. Thank you
thank
so
you.
much.
Thanks to you too. Okay, so so this was a method that was developed by them, and what we tried to do into that, what we observed that in our method, what we have done, we tried to first thing that we did is we saw that that method was of the first order convergent method. So first we extended that method to the higher order convergent iterating method by proposing this method, that is xk plus 1 equal to xk and something. And we have introduced one scalar, you can say the scalar alpha here. And in our initial approximation x0, the new scalar was the beta. I mean, what was the change from our method to that method? We have first extended that method to the higher order iteration method, and also we have taken two constants, alpha and another one is the beta. Alpha was in the method and beta was separately from the initial approximation x naught. Because what we observed that this method was becoming slow. If you are taking the beta here and if you are using the same beta here, then we were seeing that method was having slow rate of convergence. So what we did is that we chose the separate beta, though both scalars were running from 0 to 1. But the thing was that both were independent kind of things. We could choose suitable to based on our requirement just to accelerate that method. So we tried to accelerate this method that I did in my first research work, and I want to see also once again what Professor Hemant sir has done. He may also discuss that what change he has done further, because what change I did was that I introduced two constant alpha and beta, one in the initial approximation and one in the method itself, and both could be different. Here it was both same, so we were observing the slow rate of convergence for that thing. And here in this lemma we just give the property, because these properties are useful for proof kind of things. So if to prove this, we need this property of this iterative scheme that satisfies these three conditions. And this is the convergence theorem. I think I have time limitations, so otherwise I have paper. I can discuss its proof also, but I think it will take larger time. So, but basically, this is. Let me just discuss what is this result says that if you have a M cross N matrix, say A, and you are taking initial approximation x0 as beta A star, then our method will converge if this residual term is given by this x0 minus xa, right? You might have known that x is like Murray-Penrose inverse a, and x0 is your approximations, right? So ax minus ax0 kind of things are there. If its norm is coming out to be the lesser than 1, then that method was converging. And we also observed that if alpha equal to 1, then that method was having a third order convergence. In fact, that was the Newton's method of the third order convergence. And this was the error term. And in this result, the next result, what we did, how to choose the scalar beta, the same way, the way Petkovic et al. Has done in the 2011. And if you are suppose using MATLAB and you want to choose the beta, one way, there may be some other way to choose beta also. The beta which satisfies this condition, like this condition where lambda I denotes the eigenvalue of A star A. If you will choose this, automatically this will satisfy this condition. So in coding, you can use this thing. And
Sorry for interrupting, but
yeah.
what's the equation 5? Sorry.
Yeah. Hello?
Sorry,
yes,
what's the equation 5 here?
Okay. This equation five is our method that we have proposed.
Okay, I got it. Third order. Okay, I got it. Thank you.
Sure, thank you so much. Okay, so I'm not going into the proof because it will take much more time. If you are interested, I can discuss separately also. And then we had applied that time to just in some numerical experiment. We have just taken randomly generated n cross n matrix of order 128, 129, and then this is the initial approximation, and choose this alpha like that, and beta as explained in the previous slide. And this was your determination criteria, very exhaustive determination criteria. Like you see, maximum of this is less than equal to 10 raised to the minus 7, where these four are, you can see, this is Penrose conditions also. Okay, and maximum number of allowed iteration was 50. And then we just compared our method with this Petkovic method. We saw that our number of iterations, and then represent the number of iterations taken by our method, it was quite lesser than him. Just for the simplest modification. And this was the error. We also observed that the method was not convergent. Like at some point it was not converging, and we produced the method which was converging also and was fast also. Okay, and then we applied our method for several test matrices. You might be knowing that these matrices from the matrix toolbox, the matrix were of the order 200 cross 200, and their condition numbers were very high, from order 10 raised to 18 to 10 raised to 135. So, and the same thing we did. We just try to compute computational time, number of iterations. We try to compare here, see computational time with our method and his method, and number of iterations also, error also. Like these matrices, magic matrix, Clement matrix, their condition numbers also mentioned. And like Chow matrix, Frank matrix, cycle, all these matrices have very high rate of convergence, condition number. And we observed the better result. This was our first research work. And then later on, this method was also extended for any order, like 2, 3, 4. Instead, just take an arbitrary order p. So for particular value of p, like if you take p equal to 2, you may get the first or second order convergence, p equal to 3, third order, like that. So with different p, this is the most general case. For different value of p, you will get the same method with different order of convergence. Understand? Okay, so this was the research, and the same thing is that is the most generalized form, and same convergence criteria. The error terms will be different, but the choice how to choose the parameters, alpha and beta, and all those things are the same. And then we applied that for the simplest matrix. This is one simplest example I've taken. 4 cross 3 matrix, initial approximation beta A star, beta is like that. And if you apply the iteration method, that is higher order iteration method. You get this as a Murray-Penrose inverse. And then the result also applies to on randomly generated matrix from this particular interval. And here what we did, because this numerical example is for higher order iteration method. So for different value of p, we got the different order method, and then we try to compute it as a computational time. Order matrix is very small. Actually, that was very starting one. Otherwise, later on, I should take matrices of the larger order to compare the computational time. So you will also observe that if you go to the higher order iteration method, as the order increases, number of computational cost increases, though you may get the lesser number of iterations for the convergence, but the computational time may increase. Okay, so this may be one problem also to consider, that it should not increase the if you will get the more computational times, it may not be suitable for many problems. This kind of things. Okay, this is my actually last slide. Here, actually, recently, after finishing my research, I tried to apply this Murray-Penrose inverse and their technique to this particular compressive sensing problem. I think some of you might be familiar with this particular problem, signal processing, right? Like signal processing problem. I think before that, I just want to ask, you have any other queries? Because this is my last slide, and here I will just discuss about its application to compressive sensing and image processing. So any other queries you have?
Yeah, any question?
Sir, one doubt, sir, I have. I'm basically signal processing person. Basically, this whatever methodology you are saying, no, sir, Murray method, that method is meant to translate the data, or is it for compression, data compression?
This is for the data compression. That I will just give a little brief view about this thing. This will give a compression, like you want to reconstruct the signal or reconstruct the image, so that will apply to that thing. That work I have published here. Let me show you. Just 1 minute. And I think it's a very less people have worked here. This can be taken as a future area of research also. I think maximum 2 papers have came from this Murray-Penrose this topic. It's just a new area, and if you want to work, you can start working here. You see, sorry. This was the work, an improved algorithm for basis pursuit problem and its application. Basically, this is a compressive sensing problem where you want to solve again an underdetermined system of linear equations. So you see here, I have done this work into collaboration. This is the total application of Murray-Penrose generalized inverse to image processing problem and signal noise deblurring problem also. You see, this problem is this compressive sensing or basis pursuit problem is this minimization problem, AU equal to F, right? You want to get the solution where norm of U is the minimum in terms of L1 norm. And we develop method, and we apply this to, you see, onto, this is a signal problem also, and signal problem. We compared with SVD also, you see PINV, and on images also we applied this. This the method MIS2 L equal to 2 L equal to 1. This is our method. This is a PINV method. So you can see, I think it may solve your problem that we have reconstructed the images. We have reconstructed the signal also with this and this. See. Okay, so somehow we modified that method and we applied this to here in the compressive sensing problem also, this image deblurring problem and signal processing.
Thank you, sir. Thank you so much.
If anyone is interested in compressive sensing or image processing and he needs MATLAB code or something like that, then I can provide all those codes because very less paper have come from the generalized inverse area to this particular problem. So if you are interested, you may ask from. I can provide all the codes and everything in detail. And just this is the only thing I want to say, and I hope I'm able to give you some basics about the generalized inverse, some basic introduction. And I think this talk may be useful for those who are just beginner and those who already know many things about them. Maybe not that much useful for them, but for the beginner and those who wants to start working onto this research area, maybe this will be the good start for them. Okay, and this is one last thing. References, and the most important reference here is this book. The Ben Greville and Ben Israel books, Generalized Inverses, Theory and Applications. And this book is the most basic book. If you want to work onto this area, first you have to read this. So at least few chapters you have to study. If you will study few chapters, you will get the idea and then you should start working onto this area. And thank you so much. Thanks a lot for listening to me.
Yeah, thank you, Dr. Svetab. Any question? Yeah, final. So I think there is no question. Dr. Faiz is here. He's also working on this area. He can put some
Faiz
glimpse.
sir has worked a lot into this, and I am actually learning from his work also.
Thank you so much. So let me ask you the final question. Have you ever thought about improving the computational efficiency index for the iterative methods that you use in order to compute the generalized inverses?
Yeah, so far, sir, I haven't worked onto this particular thing, like increasing the, like improving in that sense. Maybe I think I should start working onto this particular thing. Because I have gone to some of your work, like you have developed some methods, like higher order method with less number of computational computations. So far, I haven't done here any work like that so far.
Yeah.
Yes.
Actually, it's important to design iterative methods which are efficient. I mean, they could be reduce the computational CPU time when we find the generalized inverses. So it's necessary to design the methods based on the minimum number of matrix by matrix
Multiplication. Yes, sir. Of course.
the another thing in your talk was about the termination condition. I think the stopping condition that you have applied, I think you considered the four Penrose equations.
Right, right.
Yeah, for your termination, that's the best way. But you know, there is a problem here. You know, if you consider the four Penrose equation as your termination criterion, the computational time would be higher, because in each iteration, when you want to compute the stopping termination, you need to compute extra matrix by matrix multiplications. And each of those matrix products, when the size of the matrices are quite high, for example, 1,500,000, you know, by 500,000, then the procedure would be difficult.
Yes, of course.
Time consuming. So you need, there are a couple of ways in literature that you can find as better stopping termination that can help you in order to stop your iterative methods without adding extra computational work to your code.
Yes, sir. Thank you so much, sir, for this session. Actually, this was my the very beginning research. Later on in my research, I stopped taking this criteria, but this was my first initially, and I followed the most traditional stopping criteria. But later on, I stopped using that thing, because I was also thinking, because it is increasing matrix multiplication, so of course it will increase more computational cost.
Okay.
And
However,
thank you so much,
for this. It's excellent. It was excellent, and thanks for your talk. It was very useful. I enjoyed that.
Thank you so much, sir. Thank you so much.
Yeah, Saurabh, your question?
Yes, Saurabh.
Sir, I have a question. I have a idea to share with both Faiz sir and Srivastava sir. I am planning. I was working in solving nonlinear matrix equations, and that one for square matrices only, and also for non-singular cases. So when we are considering that singular cases coefficients of a non-singular matrix equation, so in that case, when we are designing a iterative method, so in that iterative method, suppose we are planning for inversion iterative method, so that inverse, so can we find that inverse through generalized inverse? And if so, whether it will be it will be a good thing, or what is the cases like may arise?
So my opinion is that see, If you're working onto the generalized inverse, it means that you're working onto the most general case. The method that you have developed for the generalized inverse, okay, the same method you can apply to the matrix which is non-singular with slight modifications, right? Because that initially, like in slides also I told that what is the generalized inverse of matrix which is non-singular matrix. So suppose we have developed a method, okay, for computing generalized inverse, say Murray-Penrose inverse, and you have given me is non-singular matrix, and I'm trying to apply that method to that non-singular matrix. So of course, if you will compute its Murray-Penrose generalized inverse, it is going to come your inverse of matrix. That is true from the definition itself.
Sir, what I want to know, like suppose a nonlinear matrix equation, which the coefficient of that matrix equation was A, B, or some things. These are suppose singular. Okay. And to the solution then must be a matrix which involves that singular cases, and that's that when that in that case we need that generalized inverse idea.
Right.
So is there any research done in this area, or like how can we proceed about these things?
So I haven't worked onto this thing, but I have seen its application. Like I talked about the Drazen inverse. Okay, so I have many papers are there. If you look to the Drazen inverse solution application to the differential equation with the singular constant coefficients, you may see the application of Drazen inverse. Means to I think as far as I am considering thinking about your problem. I have seen some papers where Drazen solution for this kind of system of differential equation where matrix is the singular matrix has been taken into consideration. This is my opinion. I have seen the papers. Some papers are there. You may also do that. That's nice work.
Thank you.
Okay, thank you.
Thank you, sir. He's thinking about to merging a two different type of approach it into the one direction. Means like we like outer generalized inverse we are having.
Right.
So one means one method is there. Okay, he wants to apply this method to solve the problem of nonlinear matrix equation. He's thinking like that. So in the nonlinear matrix equation, we are developing some iteration scheme algorithm. So there we try to avoid the inversion. So instead of trying to avoid the inversion, if suppose generalized outer generalized inverse we computed and this we put into this algorithm where iteration method algorithm. So can we do this one? He's asking like that.
Yes.
From my perspective, it is like if you want to avoid the inversion, instead you want to approximate that inverse. So theoretically, it is quite possible. But for non-linear matrix equation, I haven't worked, so I cannot tell you with full detail. But I think Professor Faz sir can give you more insight into that. But theoretically, it seems to me that it is quite possible if you want to avoid inversion and you want to approximate that thing by using some iterative scheme.
Yeah, Dr. Faz, do you have comment on this? Any suggestion, Dr. Faz? Okay, okay. So we will talk to him in the second half if he will be there. So I am a doctor. I think you are having the question. Dilan, yeah.
Yes, please can you put it on the reference that you share with us?
Okay, yes. Yeah, one minute.
Okay. So is there any books written by the Indian
author? By Indian author. Yes, some books are there like R.B. Bapat sir. Old books are there, but I haven't found any new book related to that. But I am telling you, this book will not disappoint you. And if you will read this book, and if you have something to discuss, you can discuss with me also.
Actually, I saw this one, but he didn't talk about main Penrose a lot, I think. I have this book.
Okay. I haven't find any Indian author books except one from ISI professor. So separate articles are there. Like you may find some articles from different Indian resources, but not a complete book so far.
Let me specify my question.
Yeah.
If I wanna, for example, read more about the theory on more Penrose, where shall I start? Which book do you prefer?
If you want to start working on the theory part, okay, so for that also I will suggest this book, because I haven't worked only onto the iteration part of this thing. I have also published several work which totally focused on the theoretical aspect of generalized inverse. So if you want, if you can, some chapters are there like representations of generalized inverses into that book, where it has covered more theoretical part. I published one paper in applied mathematics computation. I just read that book. I just read that book, and it has given some representation of generalized inverse, various direct methods to compute direct way, like theoretical aspect to compute generalized inverse. So using that thing, I just wrote one paper, and that got published in applied mathematics computation. So for theoretical aspect also it is good, but some people also had extended the work to the grip theory, ring and field, and I haven't gone through to that thing, and so far I haven't seen any book. But my interest is also there to go to that area also, like if I want to go to the ring and field, because this same topic can also apply to that thing. This area also can be extended to that particular problem also. And other is like in operator theory, that's you can have generalized inverses of operator also. Like you have method in finite dimensional, you some with using some results you can extend that to the infinite dimension. But again, finding some books was not very easy for me, so I have to gone through some research papers, and through that I tried to prove those results, and then I got some insight. It went like that.
Okay, so thank you. So recommend me to read the papers. Thank you very much.
Yeah, yeah, thank you.
Uh, Thank you so much, Dr. Sweta, for your nice talk and basic starting from the basics. And yeah, so yeah, I learned also this all
you.
things. Yeah, so hopefully
Thank you
soon
so
we'll
much.
complete the paper.
Thank you so much. Sure. I will also read your paper now, because I'm not totally familiar with what I have done previously. So we will start working. No problems.
Yeah, so Dr. Munish is here. Because we had to take a lunch break, and then we will come back after 1 hour or whatever. We plan as a 3 o'clock. Dr. Munish.
Yes, sir. Yes.
What time we can start now? Is it 2:20?
We can start near 3:15 if it is okay to you.
Yeah, the 3:15 is fine. 3:15, right?
So I think participants can take a lunch break.
Yeah. Okay, so we can stop this session for this moment, and we'll come back at the 3:15 with the talk of Dr. Munish Kansal.
Thank you.
Yeah, thank you so much, Dr. Sweta, for your nice talk. We'll see you again in the second half.
Thank you, sir. Thank you so much. Thanks, everyone.
Okay,
Thank you,
thanks.
Shweta.
Yeah,
Very nice talk.
thanks all participants.
Yeah.
Again, okay. So with the same link, we will meet again at the 3 o'clock. 3:15, sorry.
Okay.
Okay, thank you.